Hi everyone, today we're talking about average rates of change. This will get us ready for some concepts in calculus and vectors. And average rates of change we actually talked about a lot in grade 9 when we talked about linear equations and slopes of lines. So I'm going to have you take a couple minutes and do these questions yourself and see what you remember, and then we'll take up each of these questions. So I'll just do a quick scroll through of the questions if you're doing this without a lesson copy. And you can pause each one of these and you can try each question. Okay, so we're going to start with that. Pause the video, try what you can, and then you can play again as we take these up. All right, so now that you've taken some time to do this on your own, let's go through these 6 questions to get us ready for our lesson for today. So what is the meaning of slope? So there's a couple of different things that we might remember about slope. Maybe some of them are formulas. So slope represents rise over run. We also have the formula for slope where we have the change in y over the change in x. Slope is basically the measure of, as I said in this formula, the change in y with respect to the change in x. And when we say with respect to, sometimes we just do with respect to. So the change, sorry, I should have said the change in y with respect to the change in x. Okay, and slope also measures the steepness of a line. So we know something with, like, for instance, the slope of 3 is more steep than a line with a slope of 1 or a slope of a half. So the greater the slope, the steeper the line. We can also have negative slopes as well, right? And they would be going down toward the left. Okay, so some of our questions here will use some of these formulas. So for instance, if I'm given 2 points and I want to find the slope, choose a point number 1. So let's say we call this point number 1. This would be x1, y1. Choose a point number 2. That will be your x2, y2. And then we'll use the formula above to calculate slope. So y2 minus y1 over x2 minus x1. Okay, and then always reduce your fraction. So there's our slope. We can also find it if we're given an equation and we're given 2 x values. So we find y1 and y2 by subbing in x1 and x2 into the equation separately. So to find y1, I'm going to sub in x1, which is 1, into my x's here. And then I'll just calculate. So we'll have 1 minus 2, and that will give us negative 1. So first point is 1, negative 1. That's x1, y1. And I can find y2 by just subbing x2 into our equation here. And that's going to give me 9 minus 6, so 3. So I have a point number 2 where I have x2, y2 as 3, 3. Okay, and then we're going to do the same thing that we did up here, which is I'll calculate slope by doing y2 minus y1 over x2 minus x1. So y2 minus y1, careful with those negatives and positives, is minus a negative here, and x2 minus x1. It doesn't matter which one I call point 1 or which one I call point 2, as long as I make sure I'm consistent with this one all being either x2, y2 or x1, y1, and this one for both coordinates being either x1, y1 or x2, y2. You'll get the same answer either way. Okay, and our slope for this one would be 2. Jerry charges a rate of $23 an hour to repair small engines. If parts cost $40, Write a linear equation for A, the total amount that Jerry will charge based on the time T it takes in hours to fix a small engine. So we have a flat rate of $40. So no matter what, the small engine is going to cost $40 in parts. The variable part here is going to be how much time it takes him to fix the small engine. So that's going to be $23 times the amount of hours. So if it's 2 hours, it's going to be $46. If it's 1 hour, it will be $23, and so on. Okay, this is kind of like the equation y equals mx plus b. So this is the kind of slope of our equation if you want to talk about like the rate. A balloonist travels 320 kilometers over a 9-hour flight. What is the average speed of the balloon? So we want to find the average speed of the balloon, which means over the entire trip, I'm taking a look at how far was traveled and how long that took. Sometimes the balloon might have been going faster, and sometimes the balloon might have been going slower. Maybe there was stronger wind at certain points. But on average, I can find the speed by doing the distance over the time that it took. So we'll do 320 kilometers over 9 hours. And the units are important here because that's going to tell us what our speed is measured in. And I'm getting a speed of approximately 35 this is a repeating decimal, it would be 35.5 repeated. So we'll say 35.56 kilometers per hour. Okay, so we have a table of values here, and part of the table of values is represented by time, and the other is how many hot dogs were eaten per minute by Barry at a hot dog eating contest. So what is the average rate of Barry eating hot dogs at this contest? So through the whole time of 5 minutes, the total number of hot dogs was 28. So I'm going to take the total number of minutes and the total number of hot dogs, and that should give me, if I do a division there, that should give me the average eating rate. Okay, so it'll be total of 28 hot dogs, and it took 5 minutes to eat those. So I want to know like the per minute rate of how quickly he's eating hot dogs. So I'm going to do 28 divided by 5 on my calculator, and I'm getting that he is eating approximately 5.6 hot dogs per minute. Follow-up question to this is, during which interval did Barry eat at the highest rate and the lowest rate? What were these rates? So if we look over these individual intervals, I see from the beginning to the first minute, 7 hot dogs were eaten, and then minute 1 to minute 2, 8 hot dogs are eaten here, then 5 hot dogs, then 3, then 5 again. So it looks like this 8 hot dog interval is our highest interval. So highest rate is happening from 1 minute to 2 minutes. And the rate at which this is happening is he's eaten 8 hot dogs in the span of 1 minute, right? 1 to 2 minutes, that's going to be 8 hot dogs per minute. And the lowest rate, so we had, as we mentioned above, we had 7 hot dogs, 8 hot dogs, 5 hot dogs, and 3 hot dogs, and then 5. So here's our lowest interval right here. This happens from the 3-minute mark to the 4-minute mark, where he's only able to eat 3 hot dogs in that minute. So this would be the rate of 3 hot dogs per minute. Okay, and then we have this little interesting function. We've seen each of these things before. This is a quadratic, this is a line, but we may not have seen a piecewise function before. So these are kind of interesting functions. They're one set of, there's one function that represents the function for a certain value of x, and then there's another function for other values of x. So let's focus on the first one here. My function is equal to x plus x squared wherever x is less than 2. So if I were to say this is 1, 2, 3, 4, and so on, from here this way, I'm going to graph this function. So when I create my table of values for this function, x plus x squared, I'm going to choose a bunch of values that are less than 2. And I might actually calculate the one at 2 as well, because I kind of need to know where my graph goes up to, but I won't fill that point in. Okay, so let's suppose maybe we did -3, -2, all the way up to, I'm going to do up to 2, as I said. And we'll just take each of these and we're going to sub them in each here and fill out our y coordinates. So pause the video and take a second to do that. And this is what we should have gotten. So we can actually plot these on our graph here. I'm just going to fill in my scale. And at -3, we're at 6, -2 is 2, -1 is 0, 0 is 0, 1 is 3, and 2. This one is an undefined point, but I do want to put it in just so we kind of know where to draw our function up to this value here. So this is a quadratic. It should look like a parabola. Should be symmetrical on both sides, and it goes all the way up to, but not including that final point there. Okay, so this is what our graph should look like. The vertex is somewhere in between here, and it will continue off this direction forever, but it stops right here. Once we hit this value, we're going to hop to this function right here, because this says where x is greater than or equal to 2. So now I want to finish my table of values, but I'm going to use this function to complete the rest of the graph. So I'm going to start at where I left off here, which is 2, and I'm just going to go forward from there. So this should probably give us enough. So you can pause the video and fill in your table of values, plug in each of your x's into this equation here. So this is what we should have gotten, and the nice thing is that this function actually picks up off where our last function did, so we can actually fill that in right at that point, and then we'll fill in the rest of them here. And if I've done this correctly, this should be forming a line. This is a linear equation. This is the slope and the y-intercept here. So it should be forming a line, and that would be 6, 0. So I have a straight line from here forward for the rest of the function toward the right, all the way to infinity. And that's how we graph a piecewise function. So graph it up to where the function tells you, and then continue on with your next function from there. Okay, so now that we've kind of done a recap of graphing some lines and figuring out slopes, let's talk about average rates of change. So in this unit, we're going to talk about two different types of rates of change: average rates of change and instantaneous rates of change. So let's talk about the two different types of rates of change. Average rates of change are over an interval. So for instance, when we talked about the hot air balloon was traveled over a whole interval of 9 hours. Or if we think about the hot dogs, we talked about how many hot dogs was the average rate from 0 all the way to 5 minutes. That's an average rate of change. Okay. So let's say we have a point here and a point here. If I want to find the average of how this function is changing here, I will connect those 2 points in a line, and that will represent, or the slope of that line at least, will represent my average rate of change. This is what we call a secant line. And secant basically just represents the idea that we're finding the slope of a line over two connected points on a function. Okay, so for average, we use what's called a secant line. Instantaneous is at a specific moment or at a specific point. Okay, so we were narrowing in on the idea of instantaneous rate of change when we talked about the highest and lowest intervals of the hot dog question. So the hot dog question asks us, at what times was the rate the highest, or at what times was the rate of eating the hot dogs the lowest? This is more of a closer idea to instantaneous rate of change because we're talking about like a per minute change instead of an overall change in how the hot dogs were eaten. So instantaneous is at a moment or at a point. And to measure an instantaneous rate of change at a point, we use what's called a tangent line. And a tangent line almost balances on the function evenly right at this point. So you see there's kind of like, we try to balance it so that there's equal spacing on both sides. And it's the line that just skims the function exactly at that point there. So that's what we would call a tangent line. So because of this idea of drawing this tangent line, how do I know whether it's right there, or maybe it's like more like that, or maybe it's more like that? That's why we sort of consider, in this case, instantaneous to be more like an estimated value, because maybe my tangent line might look slightly different from someone else's tangent line as I draw that tangent line. So this is more, for our purposes right now, this is more of an estimated value. Whereas this I can perfectly calculate, right? If I have 2 points, then I have an x coordinate and y coordinate here, I have an x coordinate and y coordinate here, and we can find the slope of that, and we'll all get the same answer. So we would say this one's more like a calculated rate. So how do I differentiate between average rate of change and whether I'm finding an instantaneous rate of change? So the idea for this is that we're going to use two different notations to represent rate of change based on whether we do average or instantaneous. So if you remember back from grade 9 when we found slopes, we did delta y over delta x, and we're going to keep that as our average rate of change calculation. But when I do instantaneous rate of change, we use dy over dx. And it means the same thing, change in y over the change in x, but this is just two different notations so that we know whether we're calculating an average or instantaneous rate of change. Okay, so let's talk about some different kinds of rates of change. Okay, so we can have what's called a zero rate of change, and this would mean that the slope of a line, or basically what we're calculating, the slope is 0. So think about back from grade 9, we had these like, called them constant functions because they were not changing. They had 0 rate. So this happens from any function that's y equals a number, and it will always be y equals the number that it cuts through. So let's say this is 3. This will be, for instance, y equals 3. So slope of 0, it's not changing at all. The x's are changing, but the y's remain constant. Constant rate of change means we have a consistent slope. This happens with any kind of lines that are not constant functions like what's up here. So constant rate means that it has a single slope over the entire function. And this basically only happens when I have a line. Okay, so any kind of line with any kind of consistent slope, that's not a slope of 0. Slope of 0 means it's not changing. Okay, so there's some examples. Variable or non-constant rate. This happens for basically all other types of functions. So some examples could be parabolas, exponential functions, or I can say maybe quadratics, parabolas, quadratics, exponentials, square roots, trig functions, etc., right? Okay, anything that has a curve, basically, which will be anything other than a line. Okay, and that's because, for instance, if I have a curve, then of course I can't have one singular slope here, and I have all these different, maybe tangent lines that are sort of going along here that are all different slopes. All right, so let's take a look at calculating some average rates of change. This is a parabola, so this is one of those variable rates that we talked about above. So it depends on what interval I take the rate over. So find the average rate of change over the interval from 2 to 5. This is representing our first x and our second x of the interval. So remember, when we use interval notation, it's an x to an x. So I need to find the y's that are associated with this so that when I look at my quadratic, I can actually find the slope of the secant that goes over this function. So if we were to just look at a visual here, this is a quadratic with vertex at 3, -1, opening up, so it looks something like this. And if I want the slope of, or the average rate of change from 2 to 5, it will probably be something like this, right? And I'll have a line going from the x value 2 to the x value 5. And I'll have to find the y coordinates that match up with those and find the slope of this line. Okay, so let's find the first y by plugging in f at 2. We're going to get -1 squared, which is 1, and then 2 minus 1 is 1. So I have a point at 2, 1. So I drew my picture slightly incorrectly then. I have actually a point that's up here. So maybe my quadratic looks more like this. Okay, we'll just erase this just so that we know we have the correct values here. This is the correct value. x1, y1, and then I'm going to find f at 5 so that I know the y value at that value. So 2 squared is 4, times 2 is 8, minus 1 will be 7. So I'll have a second point at 5, 7. This will be x2, y2. And average rate of change we denote by doing delta y over delta x. This basically just means change in y over the change in x. y2 minus y1 over x2 minus x1. So that's going to give us 7 minus 1 over 5 minus 2, which is 6 over 3, giving us a slope of 2. If there's any units of measurement, you can put units of measurement, but in this case, we don't have any units, so it's just slope of 2. Okay, same thing that we were doing before back from grade 9. It's just delta y over delta x, find your 2 points, and calculate the slope. All right, another quadratic that has variable rates here. So the height h in meters, this is the height right here. T seconds, so this is time in seconds, is modeled by our equation h at t, and here's our graph right here. Determine the average rate of change of height of the ball for each time interval. So I'm finding how the height is changing with respect to time from 0 seconds to 0.5 seconds. So for this interval right here. So let's look at a visual of what we're trying to find. So I'm trying to find the slope of the secant line from 0 to 0.5, which is approximately like right here. So if we were to take a line function here, and let's draw a line from here to here. I'm trying to find the slope of this line. So this point I can actually pretty clearly see is on an exact point here. 0 is equal to 1, and that's easy to calculate as well. Okay, we can calculate this pretty easily as well. If we're not sure, we evaluate h at 0. Of course, that means this is 0 and this is 0, and all I'm left with is 1. So we have the point 0, 1. And then I'm not exactly sure that this is on an exact cross-section right here. So I think we should actually just calculate that one in the function itself. We have the equation here. So we'll evaluate h at 0.5. Remember, this is time 1 and time 2 when we talk about the interval. So you're going to enter this into your equation to find the y coordinate. We'll do this one below here, so you can use the space over here. And we'll take a moment and just quickly plug this into our calculators here. And we should get 6.775, and this is meters. So our second point here is 0.5, 6.775. So this is time 1 and height 1, and this is time 2 and height 2. So we're going to find the change in height over the change in time by finding the slope of this secant line right here. So h2 minus h1 over t2 minus t1 Okay, plug that right into your calculator, and you should get about 11.55, and this is height over time, so meters over seconds. So meters per second. Okay, for our second one, we want from the interval from 1 to 2.5. So here is our point at 1. Again, not quite on an exact cross-section, so I'm going to use the equation to calculate that one. And then 2.5, also not on an exact cross-section, and I want the slope of the secant line that connects those two. Okay, so in order to do this, I need to find the heights at both of these times. So think of this as your time 1 and your time 2 for the secant line. So let's just start by evaluating h at 1 and h at 2.5. So 15 minus 4.9. We get 10.1 for this one, meters, and then plug in 2.5. So this will give us 5.375 meters. So here we have our 2 points, 1, 10.1, and 2.5. 5.375, and you can look at your graph as well. We have a graph to help us with this, so look at your y coordinates, make sure that these values that we just got make sense, and let's calculate delta change in height over the change in time. So let's call this T1 H1 T2 H2. It'll be 5.375 minus 10.1 over 2.5 minus 1. And that should give us negative 3.15 meters per second. All right, and final question here is the height of the ball changing at a constant rate? And of course, if I calculated the height of the ball, how the height of the ball changes over two different intervals and I get different answers, I can clearly see that the slopes of the secants are changing. constant rate would have to be just a straight line, and then that means that the change in height and the change in with respect to the change in time will be the same all across the function. Any curved function like this, where we're getting different rates of how the height of the ball is changing, that's going to give us a variable rate. So no, the height is not changing at a constant rate. We'll say it's changing at a variable rate.